Is there any comment or question about this list of questions here? Let's start with that. Have you already found the answers to any of them? According to the session of yesterday? That's one. Okay. Was it yes or no? All right. Any other one? Well, I hope that you have already understood what the answer to this question is. We haven't discussed the answer to this question. The Big Bang. Yesterday, somebody asked me about the Big Bang. Probably we can start with this today with the Big Bang. Where is the Big Bang idea coming from? The idea comes from the fact that, as I mentioned yesterday, the scale factor is a function of time, the metric, and this we are observing that the galaxies are receding from us, so that we also observe a redshift in the light that they emit. That means that the scale factor is a growing function of time. So the universe is expanding. That means that in the past there must have been a point, a moment in time in which the scale factor was probably 0. So now it's growing. If you go to the past, the scale factor is a decreasing function of time. And well, we are expecting that the scale factor should be positive, definitely. So the minimum value that it can take is 0. So this opens the possibility that the scale factor is 0, and at that moment in time, we call it the Big Bang, the beginning of the expansion of the universe. So this is more or less a formal expression, because we are not yet sure that that moment actually happened. But according to the calculations, the possibility is there. And that's the moment that we call the Big Bang.
What if the scale factor is not 0 at t equals to 0, so it's, let's say, another number from 0?
Yeah, there is also that possibility. There are some interesting ideas about the early universe related to inflation and some other models, in which the minimum value for the scale factor is not 0, but just a very tiny value. That is quite possible. But we have not yet any signature, not any signal that the scale factor was a finite number at the beginning of time. So the possibility that it was exactly 0 still is, right? So probably you remember that yesterday I showed you the integral to calculate the age of the universe, and the lower limit for the integral was 0. So we are taking that into account. So so the Big Bang, according to this idea, is just a moment in which everything goes up. The universe has an infinite density, and the scale factor is 0. So at the beginning, when this idea was put forward in the early 20th century, people believed that the universe started in a single point. So everybody thought that, okay, everything and everybody in the universe was just collected in a single point, and then the universe started its expansion from this very point. But that is not quite correct, because according to the cosmological principle, I'm entitled to say that everything started from this point because I can see that galaxies are moving away from me in an isotropic way. So in the past, probably they were coming. If you try to imagine that you are time backwards, you will see that the galaxies are coming to my position. So I can say that, well, the Big Bang happened at this very point I'm standing on. But another being in another galaxy will see the same phenomenon. That all the galaxies, if you move the time, if you try to move the time backwards, all the galaxies are going to gather in the point that he is standing on, right? And the same thing is going to happen to any other being, intelligent being in any other part of the universe. So everyone in the universe will say that the Big Bang happened in the point they are located. So the conclusion is that the Big Bang happened everywhere in the universe, not in a single point. Right? So the Big Bang is called a singularity that happened at a very single moment of time, and it happened everywhere in the universe. This is in contrast to the singularity in a black hole. A singularity in a black hole is a singularity that happens in a single point in space, and it happens forever and ever. I mean, this singularity is always in the same position for all the time. The Big Bang is the opposite. It is something that happened in a single time in the evolution of the universe, but it happened everywhere. Is it clear for everyone?
Like a mystery, how it happened.
Yeah, we don't have any idea what happened exactly at that physics alone are not able to handle infinity quantities, right? Like an infinite energy density, infinite temperature, and so on and so on. So far, it just remains as a mathematical possibility, right? But we don't have any reliable theory to tell us what happened exactly at that time. So it didn't happen at a single point. That's the answer to this. How could the Big Bang create an infinite space in a finite time? Right? What do you think is the answer to this question?
I don't know if this question is separate or split the time in space.
Well, in any case, even if the time and the space are more or less of the same kind of thing, like they are coordinates, in any case, you can separate the definition of time from that definition of space, right? So there is a clear distinction between the two. So it is possible to say something about the space, even if you are not referring to the time at the same time.
You just gave that answer by saying that the Big Bang occurred everywhere, so it must have been infinite already since the beginning.
Yeah, the space was already there, right? Only the scale of the universe was very tiny. But the universe was already there, the space was already there, and from that point it only expanded. Right? How could the space not be infinite? Is there any possibility to have a non-infinite space? Probably this question was motivated by the thought that probably most people think that the universe must be infinite. Or have you ever thought about a finite universe? with a finite size? Or do you think that the universe should be, must be infinite in extension?
That would be a bit contradictory to the main idea that the Big Bang occurred everywhere. Just by thinking that if the Big Bang is a singularity that happened everywhere in space, then by necessity, by what we see in the isotropic space, is the distances that are growing in everywhere and every point, makes us think that it must be infinite. It should be. Otherwise, what we are gonna be measuring won't be isotropic.
What do you think, the rest of you? What do you think of that? According to the session yesterday, the universe must be infinite. It can be a closed universe. In that case, the space is finite. So the cosmological principle just gives you three possibilities: a flat universe, a closed universe, and an open universe. The flat and the open universes can be infinite in extension, but the closed universe should be finite. So there is no logical necessity to have an infinite universe, according to the cosmological principle. Right? Okay. So today I promised you that I was going to talk about the distances in the universe. So yesterday you had some lectures on general relativity, and many of the things that we were discussing at the end of the last session, yesterday, were related to general relativity more than to cosmology. There are no markers. So you learned yesterday some general relativity, right? Okay. All right. So what is the notion of distance that we have in general relativity in a curved space-time? So I'm going to talk about one of them, because there are other options. So again, you have the line element here. So one possibility is that we can talk about the proper distance between two locations in space. This is the metric in special relativity. So what I'm thinking here is about this difference between 2 points in the space with coordinates x2 and x1. Right? How can we calculate that? Okay. So what you have to think here is that you are going to stop time. So we are going to choose a time t equals to t naught, just to have a number here, so that tt is equals to 0. So the time is not going on, right? It is not moving. So in that case, this quantity is going to measure the proper distance between 2 points in space. In the case of special relativity, this is very clear. The proper distance between 2 points is just the difference of their location in space. I mean, what is the proper distance between this point in the board and this point in the board? You have just to take a rule and to measure the distance between the 2 points. And that's it. That's the proper distance. Right? But what happens when you have an expanding universe. In the case of an expanding universe, the metric, for the sake of simplicity, is this one, right? So what is the proper distance between 2 points? In this case, it is going to be this quantity. So the proper distance, I'm going to use another variable here, is going to be the scale factor by the separation by the difference in the coordinates of the points in space. So because the scale factor is a function of time, you will see that the proper distance between 2 points in space is going to change with time. Right? At the present time, we take the normalization condition that the scale factor is 1. So the distances between different objects in the universe today, the coordinate distance between 2 objects in the universe today is just the proper distance. But in the past, you have to take into account that the scale factor was smaller than it is today. So the proper distances between objects in the past was smaller than it is today. Right? So what happened at the beginning of time, at the time of the Big Bang? The scale factor at that time was 0, so the proper distance between any pair of objects in the universe was 0. That's why people think about the Big Bang as happening in a single point. No, it didn't happen in a single point. But it happened at the moment in time in which the proper distance between any pair of objects was 0. Right? And you can see then that here, for instance, this is an example in which you can see the meaning of the expansion of the universe, that the proper distance between 2 pairs of objects in the universe is growing with time because the scale factor is a growing function of time. Right? And that's the meaning of the expansion of the universe. Any question? No? Okay, now for the answer to this question, if the universe is only 10 million years old, how can we see objects that are now 30 billion light years away? So, so let's calculate this quantity here. Imagine that you want to calculate the proper distance between 2 distant galaxies today. But the only way that you can try to measure that, okay, you cannot take a big rule and try to measure the distance between these 2 distant galaxies, right? We cannot go beyond Earth to do that. So how can what is the object that we can use as a rule to measure distances in the universe? How can we try to measure distances in the universe? With light only. So let's go back to the line element. Right? And we want to measure this quantity using light. But we know that light is going to move in the so-called new geodesics. So we can calculate this quantity here using the geodesics the light is moving on. So I'm going to take this quantity to 0, and you can see that dx is going to be dt over the scale factor. Right? So if I want to measure this, I can integrate. And so from x1 to x2, so on the left-hand side, I have the interval for the distances. And on the right-hand side, I'm going to have from 0 to t, and I have to integrate this quantity. Right? And what is the proper distance? This is going to be the proper distance between 2 different objects in the universe today. So you can see that we can measure this quantity, this proper distance here, by having an integration in time on the scale factor. Actually, I can try to change this into an integral to the scale factor, and in this case, I will find the proper distances. Try to imagine the case in which the scale factor is not a function of time, which is just a constant here. Try to imagine that the scale factor is just 1. So this distance here is going to be proportional to the time interval, right? Sorry, remember that here I'm working on units in which the speed of light is 1, so I'm going to write explicitly the speed of light here. So the proper distance is going to be just the speed of light times the time the universe has evolved from the Big Bang up to the present time. Right? So in that case, if this is going to be 1, if the universe is 10 billion years old, the proper distance would be, just to say, the largest distance that we can measure in the universe would be 10 billion light years. Exactly. But because this is a function of time, this integral here is not going to give you just the time interval. Because this quantity here, the scale factor, was smaller in the past. So if you try to do this integral here, you will find that this quantity is larger. The quantity, the answer, the result of the integral on the right-hand side is going to be larger than just 6 times the time interval. It is going to be larger than that. Can you see that? This is because this is going to be less than 1 in the past. Is it clear for everyone that this is going to give you a result which is larger than this, just because this was smaller in the past? So the answer to this question is this is quite possible because the scale factor has been a growing function of time since the time of the Big Bang. So it is quite possible that the universe is just 10 billion years old, and the most distant object that we can see could be 30 billion light years away. This is quite possible. Actually, if you try to do the right calculation, you will find that the distance to the most distant object in the universe that we will be ever able to see would be something like 42 billion light years. And more or less, that's the size of the universe, 42 billion light years in radius around us.
Can you say the distance again? The diameter?
Yes, this is the distance between two pairs of objects here. So is it clear for everyone that the objects are farther than the distance that the light has traveled, so to speak? Again, if the universe is 10 billion years, what is the distance that the light has traveled in that time in the universe? If the age of the universe is 10 billion years old, what is the distance that the light, a ray of light from the Big Bang has traveled up to the present time? What is the answer? 10 billion light years. No, that's not the answer.
Depender de lo que
Yeah, but the answer is 10 million light years, which is not the right answer. What is the distance that the light has traveled for the full evolution of the universe? What is the answer?
Or it can be the light.
That one over here, because we calculated this thinking about a ray of light. So this is exactly the distance that the light has traveled from the beginning of time up to the present time. So the light has traveled 42 billion light years, not only 10 billion light years. So how is it possible that a ray of light has traveled faster than light? Because at the same time that the light was traveling in the universe was in expansion. So try to imagine that a thought experiment in which there are two of you here, one located here and another one located here, and I'm a ray of light departing from here, so I'm traveling towards the other person here, but at the same time I'm traveling, these two people are moving apart, right? So at the time that I arrive to this point to reach the person over here, the person over there has already moved to that in that direction. So the proper distance, if I try to measure the distance between the two people here, the distance will be larger than just my speed times the time that has elapsed between the two events. Is it correct? So you have to think about the expansion of the universe too. So light has traveled more than you could have thought if you don't take into account the expansion of the universe. Correct? Any question? Because I can calculate this integral over here. If I know the exact number for the universe, which we are going to discuss in this session, you already know what the function of time goes here exactly, and then you can calculate this integral, and you can get the exact number. Any other question?
So you can declare that using that calculation in some point of the universe.
No, I have to calculate that by solving this equation. In order to have the function of time for the scale factor, I have to solve the Einstein equation. So I have to solve this differential equation for the scale factor, and in order to do that, I need to know the energy density in the universe. If I know the energy density of the universe, we can calculate everything. So for almost 100 years, it was almost impossible to know exactly what is the energy density in the universe. So it was just recently that we could measure this quantity, and from that point we could calculate everything for the scale factor, and we can calculate the age of the universe exactly, and we can calculate the extension of the universe and many other things. So, but I have to solve Einstein equation.
How did we measure the energy density of the universe?
That's what we are going to do now. So it is going to be a long answer. So it is coming now. So we are facing one of the most important questions for humanity. What is the universe made of? So the very first answer to this question is that the universe is made of the chemical elements. So there are 100 so chemical elements that we have identified on Earth. So the first answer that you as educated people can give is the universe is made of the chemical elements, right? Hydrogen, helium, and so on and so on and so on. Oh, these are the elements that you can find on Earth. So according to the cosmological principles, these chemical elements should be everywhere. And we have evidence that this is true, actually. How do we know that these elements exist more or less everywhere in the universe? Sorry? spectroscopy of who? Of quarks, stars. Because we already know that the stars are very similar to our sun, in the solar system. So if the physics of the sun works very well to explain the behavior of the sun, so we are very confident that this is going to work for every star in the universe, and we see stars everywhere, and these stars have a spectrum very similar to that of the sun. So, yes, it is correct. There are chemical elements everywhere, but if there are chemical elements everywhere, there should be, these particles should also exist everywhere in the universe, because we know the chemical elements are not elementary particles, but the elementary particles are these ones over here. You are going to discuss much more about this in our session, but just for today, just keep in mind that we have 17 things that can explain many of the matter elements in the universe. It is not 100 and so. It is just 17 things to explain the type of matter we are very used to. So this is one answer. But we have to calculate the density of these things in the universe, because the Einstein equations require the energy density, not that we identify the type of matter that exists in the universe. So how can we calculate the energy density of this type of matter? So for that we have to go to the so-called theory, the Big Bang theory, not a TV series, but this serious thing in cosmology. And there are two main assumptions to make the calculations here. We are going to assume that the distribution function, we are going to imagine that in the past, the universe was very hot, that had a very high temperature in the early universe, and in that case, we will have a soup of particles of fundamental particles which are very relativistic. So one very good guess about the particles in that stage is that the distribution function for the photons and neutrinos is going to be the one of an ideal gas, a relativistic ideal gas. So you are going to assume that the distribution function for photons and neutrinos is going an ideal gas, relativistic ideal gas, which is just the black body. Well, for the photons, it's the black body. For neutrinos, as they are fermions, it's not the black body, because this is going to be a fermion gas. And this, the form of the distribution function, is going to be preserved by the expansion of the unit. So this can be shown very easily by working on the Einstein equations, but for now, I will ask you just to believe in this. So, one question for you. Why are we talking here about the distribution function? What is the importance of the distribution function in physics? Is it an important function? Is it not? Is it better to talk about density? Is it better to talk about mass or whatever? Why are we talking here about distribution function? How do you believe the reason is for this? Yeah, more or less, that's a partial answer, but it's not the complete answer. Why the distribution function is important in physics? Because it tells us all the important things about the matter we are interested in. In the distribution function, you will have all the information about the matter here. In this case, about the photons and the neutrinos. You don't need anything else. And we already know that the distribution function is going to satisfy one fundamental equation in physics, which is, what is the name of the equation of motion for the distribution function in physics? The Boltzmann equation. Yeah? Well, probably you didn't know that it was a fundamental equation, right? It is a very important equation. It is very difficult to solve, but in any case, it is important. For instance, the black body for the photons. Probably you have heard that the black body distribution function for the photons is a solution for the Boltzmann equation. Have you heard about that? This black body distribution, it is a solution of the Boltzmann equation. Actually, it is the stationary solution of the Boltzmann equation without collisions. If you take away any collisions in the Boltzmann equation, you will get the equilibrium configuration, which is for photons, the black body distribution, and for neutrinos or for any fermion particle, it's going to be the Fermi-Dirac distribution. So they are solutions to an equation. All right, so we are going to assume this, and for the atoms, we are going to assume that they will be an ideal gas, but in a non-relativistic way. And the form of this distribution function is going to be preserved again by the adiabatic expansion of the universe. So if you take these two assumptions into account, you can work out all the details for the formation of atoms in an expanding hot universe. So I'm going to show you how you can do that in detail, more or less in detail. So you have to imagine that at the beginning you have a relativistic soup of protons, neutrons, photons, and neutrinos, and we are going to calculate more or less the amount for the formation of primordial elements, basically hydrogen, deuterium, helium, lithium, beryllium. And for that, we only have to do, the only thing that we have to do is to apply particle physics, the particle physics that we understand very well according to physics, to an expanding universe in a very high frequency. So everything is going to come out as a result of the particle physics we already know. And for that, we will have to account many constants, and these constants, these fundamental constants in physics, have been measured in terrestrial laboratories, like the gravitational constant, the lifetime of the neutron, the fine structure constant, the mass of the electron, the energy, the binding energy for the hydrogen atom, and the mass for neutrons and protons. So we have to take all these quantities into account, and from these constants, fundamental constants, there will be a definite answer for that. So there are some stages for this calculation. The first one, as I already told you, there will be a relativistic soup of particles. So basically, these are the main interactions that you will find between the particles. So you have a neutron plus a neutrino, and they are going to split into a proton plus an electron, and vice versa. So also you can have a neutron plus a positron. They are going to be converted into a proton plus an antineutrino, and vice versa. And the same for these two other interactions. A neutron is going to decay into a proton, an electron, and antineutrino, and electrons and positrons are going to annihilate, and there will be as a result the emission of two high energy photons, and vice versa. So these interactions are happening at this stage in the evolution of the universe, and they are there to maintain the thermal equilibrium between the different particles. So everything is in thermal equilibrium here, because these interactions are happening fast enough to keep that thermal equilibrium. Okay, this is the first stage, but at the time, more or less around 1 second, or a temperature with about 10 to the 10 Kelvin, there is a very interesting phenomenon here, which is the decoupling between neutrinos and baryons. And by baryons here, I mean protons and neutrons. Right? So there is a first decoupling between the neutrinos and the baryons. This is the origin for now theoretical neutrino cosmic background. So one prediction from this phenomenon here is that there should be a neutrino cosmic background. In the same way that we already know that there is a photon cosmic background, there should be a neutrino cosmic background that we haven't detected yet. But it is there. It should be there according to the particle physics theory. So, because this decoupling between the neutrinos and baryons means that all the interactions in which the neutrinos are involved are not happening anymore. So this interaction is switched off, this interaction is switched off, and this interaction is switched off. At least for one of the directions for interaction. For instance, this is a very important one here because the interaction the result from the interaction of a proton, an electron, and a neutrino is not happening anymore. So the only thing that is happening for this interaction is that the neutrons are decaying. The neutrons are disappearing into protons, electrons, and more neutrinos. But it is not possible to make more neutrons because the inverse interaction here is not happening anymore. So this is very important. Because why? Because neutrons and protons have more or less the same mass, right? Which is larger, the mass of the neutron or the mass of the proton? Well, from here you can see which mass is larger, right? Which mass is larger? The neutron, because the neutron is made of a proton plus an electron plus an antineutron. So obviously, the neutron mass should be larger than the proton. Okay, so because of this, but in any case, the masses are very similar, very, very similar. That means that the number of neutrons and the number of protons is roughly the same in thermal equilibrium. But because of this decoupling between neutrinos and baryons, this is not going to be true anymore, because the neutrons are going to decay into protons. So what is happening here is that there is going to be more protons than neutrons as the evolution of the universe proceeds. Okay, is that clear for everyone here? So there is going to be an imbalance between the number of neutrons and the number of protons because of this decoupling between neutrinos and baryons. Well, you have to keep in mind that the photons in this relativistic soup are so relativistic they have such high energy that the formation of atoms is not yet allowed. So there are no atoms here yet. We have to wait until the next stage. Any questions here? Okay, let's go to the third stage. So the third stage happens around a time of 3 minutes here, and a temperature of around 29 Kelvin. And what you have here is just a relativistic soup made of photons and electrons. This is the only interaction that still survives at this point in the process. That you have the annihilation of electrons and positrons, and you are producing from that two energetic process. So the process that is happening here is that you have the formation of the first atomic nuclei in the evolution of the universe. How this is going to happen? Because the neutrons that are around are going to be captured by other protons. And for instance, the first element that you are going to, the first element that is going to be formed here is deuterium. Do you remember the composition of the deuterium atomic nuclei? What is the composition for the atomic nuclei here in deuterium? That's right. So it is the simplest nuclei that you can form. Just a proton and a neutron. And from that, you just start to put up other chemical elements. And one of the most important in this case is the formation of helium. Because helium is a very stable element. Once it is formed, it remains there for a very long time. So one of the main predictions here for the process of nucleosynthesis for the Big Bang theory is this number here, which is called the ratio between the helium abundance over the hydrogen abundance. So we can calculate for the quantities I'm showing here, how many atoms, how many helium atoms there are per hydrogen atom. So it is this quantity here, which is more or less 1/4. So this number here, 1/4, comes from this other number here, which is 1/7. And you can see here that this quantity here, 1/7, means that there are 7 more, the number of neutrons is 1/7 the number of protons in the universe. Remember that I told you that at the beginning, these numbers were roughly the same. But because they are disappearing, at the end of the process, there is going to be less neutrons than protons. Right? This has many consequences. The first one is that you cannot build up many helium atoms that you would like to, because there are not enough neutrons around. If there were the same number of neutrons and protons, probably you can form a lot of helium atoms, right? Because for form a nuclei for the helium atom, you require 2 protons and 2 neutrons. But because they are not in the same number, you cannot build up many helium atoms. Just 1/4. And the rest of the protons are just wandering around alone, and they are going to form later hydrogen, because there are no more neutrons to build up heavy chemical elements. Is it clear for everyone? Yeah? So this is a very important prediction. This prediction was made in the 1950s already. And at that time, the Big Bang theory was not accepted yet for the community community. So Gamow, which was one of the first to do this calculation, said, okay, if there was a Big Bang and the universe was very hot in the past, so one prediction coming from particle physics is that the contribution of helium atom over hydrogen atom should be this 1/4. That was a very clear prediction of particle physics in an expanding universe. And the prediction remained there for a long time until we were able to measure it. Okay, I'm going to show you a next slide. But for now, let's go to the last stage in this calculation, which happens at the time of 300,000 years and a temperature 10 to the 3. what happened at this stage was the decoupling between photons and electrons. So the photons were not energetic enough to be coupled to electrons. And the big consequence of this is that every electron and every positron in the universe annihilate at that point, and they left behind a sea of photons, which we now call the cosmic microwave radiation. So the photons of this cosmic microwave radiation were originated at this stage in the evolution of the universe. According to particle physics, these photons were created when the universe was around about 300,000 years old. So these photons, probably you already know more or less the age of the universe. Right now, it is around almost 14 billion years. So these photons have traveled from this time to the present time. They have traveled for around 13,000 years. And we are collecting right now these photons on the surface of Earth. This is quite impressive. And what I mean for this is that a photon that we are collecting right now was originated right here. This is quite amazing, isn't it? Because a photon traveling for such a long time on this scale. Okay, but what happens for this annihilation between electrons and positrons? Well, the thing here is that if the number of electrons if the number of electrons were the same as the number of positrons, so there would have been any electrons left if these numbers were the same. But we already know that there are electrons in this universe. And we don't observe enough positrons in the universe. So that means at this time, every positron that was already in the universe annihilated and disappeared from the history of the universe. And there was only, the only survivor here was the electron. An estimation is that at the beginning in the universe, there was 30, something like 30 million electrons, sorry, 30 million positrons, and 30 million electrons plus 1. So there was a very tiny imbalance in the number of electrons and positrons in the universe. A very tiny. For every 30 million electrons, there was, sorry, for every 30 million positrons, there was 1 electron in excess. And those electrons are the survivors that we can find in the atoms everywhere in the universe. So this is just theoretical, but this is a very strong prediction coming from particle physics in an expanding theory. So what you are doing here is joining two fundamental theories in physics: particle physics and general relativity. Any question? Yeah, there might be a fundamental reason for that, but we don't know why yet. Because the standard model of particle physics predicts that for every possible process for the creation of electrons, you should also create positrons with the same number. So the standard model of particle physics cannot explain the imbalance between electrons and positrons in the universe. Yeah, there might be something there. We know that there should be some broken symmetries in the universe, but we don't know how they were broken. Because in the standard model, we don't know any mechanism to do that. Any other question? Okay, but you know, for theorists, the world is very clear, but for experimentalists, this is not so clear. So you you can see in this slide the predictions for the different amounts of different chemical elements with respect to the number of hydrogen atoms. At the top, you will see this quantity for helium, this quantity for deuterium, for helium-3, and for lithium-7. So every curve here, this is for helium, the first one, the second one for deuterium, the third one for helium-3, and the fourth one here is for lithium. So these are the theoretical predictions, and the only free parameter in the model to have a definite answer for that is a so-called variant to photon ratio. So this quantity means the variant to photon ratio is how many atoms there are over the number of photons. In order to calculate this number, you have to measure how many atoms there are in the universe and how many photons there are in the universe, and calculate this ratio. If you can do that, you will find this number. The theoretical expectation is that this number is in between 10 to minus 10 and 10 to minus 9. This means, okay, Roy, you can help me out with this. There are around 10 to the 9 more photons than atoms in the universe. Can you believe that? For every atom in this room, there should be 1 billion photons in the universe. But what is the exact number? Okay, this exact number was not very well known in the past. It was until the Wilkinson map collaboration measured with high accuracy the anisotropies in the cosmic microwave background that this number was calculated, was measured, not calculated, but was measured with a very high accuracy. So the measure of this quantity is this thin yellow line. So this means that you already know how many photons there are for every atom in the universe, right? This is the number. You must be amazed because of that, because in some sense you have counted how many atoms and how many photons there are in the universe, and probably you don't know exactly the number here or the number here, but you know the ratio between the two.
So this is why recommendation happens so late in our universe.
By recommendation, you mean the formation of atoms, right? Yeah. Because there were so many photons that the electrons were not able to be captured by the protons to form atomic nuclei. Yeah. Any other question? So, if you take this number here, so the theoretical prediction would be this one here, which is more, a little bit less than 0.25 here for the helium contribution, and the gray shaded region here is the direct measurement of this quantity in galactic clouds in the Milky Way. So this is a direct measurement in clouds in the Milky Way, and this is the measurement from the photons in the microwave background, the vertical yellow line, and you will see that there is a very good agreement between theory and the measurements. So this means that we have a very nice account of the number of photons and atoms in this field. And from this, well, I'm not showing the quantity here, but from these measurements, you can calculate the energy density that exists in terms of photons and in terms of atoms. So if you can calculate this quantity, you can estimate that quantity from here. You can put that information in the Einstein equations. And from that, you can try to calculate all the integrals I showed you in these boards. Because you already know what the energy density is. So you can calculate everything from that. Any question?
I have one. How, well, what's the procedure that they use to measure that yellow line?
Okay, I'm going to explain it in the following slide. So you wait for a little bit, you will know the answer. Other questions? Okay, I'm going to skip this slide because we are running out of time. So I'm going to explain some of the physics behind the cosmic microwave background. This background was discovered in 1965 in this famous experiment by Francis Wilson, which was a serendipity discovery here. And they discovered that there was a background. And they were able to measure one point of the spectrum of this background. And from that point, they calculated the temperature of this background, which is about 2.7 Kelvin. Very low temperature of this one. But in the 1992, there was this COBE satellite that was able to measure not only the temperature of the background. I mean, it was able not to measure not only one point, but many points in the spectral distribution of the background. And from that, they measured that there should be a small deviation from the black body spectrum of this size, 10 to minus 5. So if this is the temperature of the black body, 2.7 Kelvin, so there are tiny differences. So the background is not exactly a black body, but there are tiny differences that are of this order, 10 to minus 5. So this was first measured by this satellite here, and there were another important satellite in 2003 that measured with a very low quality, with a very high quality, the same anisotropies that were discovered here. You can see the difference between the two images here. This is a more fine measurement of the anisotropies. So if the cosmic background were completely isotropic, it would look like the first picture here. But it is not exactly isotropic or homogeneous. There are tiny differences everywhere. But the differences, the blue and the red regions are not very large differences. They are of the same order that I'm showing here. So the differences are very tiny. And there was another satellite, a Planck satellite, that measured with a larger accuracy these tiny deviations, these tiny anisotropies in that cosmic microwave background. So you can see here in the colors, in the line of colors here, that the differences between different points in the picture is of the order of 500 microkelvin. So if the temperature, the mean temperature is 2.7 Kelvin, that differences are at most of the order of 500 microkelvin. So this is a very impressive measurement, right? Because you are measuring a black body radiation with a very low temperature, 2.7 Kelvin, and apart from that, you are also measuring tiny differences of the order of microkelvin in the space. You are not doing that measurement in a terrestrial laboratory. You are doing it in space. Question? Well, but this is so many things arise from this measurement. So this is more or less the theory behind that. What you have to do is to make an expansion of the tiny differences in terms of spherical harmonics in the sky. So what you are trying to do is to have a quantitative measurement of the difference between this point on on this direction of the sky sphere, and from this point on the sky sphere, and so on and so on. From different points, we have to make a measurement of the differences of the photons coming from this direction, coming from this other direction, and from any other direction around us. So to do that, you have to do this expansion in spherical harmonics of these tiny differences, and the variables here are the two spherical angles, theta and phi, and what you have to do is to try to determine, in order to find this expansion, you have to determine this constant coefficient, right? So in order to measure these constant coefficients in the series expansion, you have to do some measurements. So you have 4 pi radians squared for the whole sky sphere, and this is the resolution of your experiment, because the experiment is not perfect, it has a finite resolution. So the number of independent measurements that you can do for these coefficients here is quite limited, and it is this quantity here. Because of the resolution of the experiment, there is a maximum L in this expansion that you will be able to determine. So you can see if the resolution of the experiment is perfect, I mean this quantity is 0, the limit in the number of coefficients that you can determine is just infinite. You can determine all the coefficients in the expansion. That's why we're required to have very accurate measurements of the tiny differences in the cosmic microwave. So this is what you have to do. There is a statistical process to do that. The mean of any of the coefficients in the expansion is 0, but this correlation between the coefficients is not 0, and the quantity, the important quantity here is this CL, which is, I mean, the amplitude of this correlation here, and this is what you have to measure. So the measurement is not directly from this quantity here, but about their correlation here. In terms, this L that is here is just the L of the spherical harmonics over there, and the error in the measurement is given here. The error in the measurement of each of one of these coefficients is given by this quantity, and it depends on the number L of the spherical harmonics. So this is very important, because if L is very large, you will see that the error in the measurement is very tiny. But what happens if the L is small, like 1, 2, or 3? You will find that the error is going to be noticeable, or quite noticeable in the measurement. Any questions here? So you have a series expansion, and you only have to determine every coefficient in the expansion from the measurement that you are doing over the cosmic microwave. Easy, right? Well, and the result is given in terms of this plot over here. So what you have here is the multiple moment of the series expansion, the L in the series expansion in the horizontal axis, and on the vertical axis you have the amplitude of this correlation between the coefficients in the series expansion. And this is the result. The points in this figure are the experimental points, the observation points. The points that were measured here by the Planck collaboration. So you can see that the error in the measurement for low values of L, the multiple moment, is very noticeable. But this is unavoidable. We cannot, there is no way to make these errors smaller, because this just comes from theoretical expectation. But the error for large values of L is very small. This is called the angular spectrum of the anisotropies in the cosmic microwave path. And this is one of the most famous figures in cosmology. Interestingly enough, there is a series of peaks here. which are very important for the interpretation of the evolution of the universe. So the peaks, the position of the peaks is more or less very well understood because, it is actually very well understood because you only have to calculate the so-called sound horizon. And this sound horizon is the distance that the photons and the atoms travel from the beginning of time, from the beginning of the expansion of the universe, up to the time in which they were decoupled, until the photons decoupled from the electrons of the pulsar. So you only have to calculate that distance, the distance that these two things together travel at that time. So this is something that we can calculate very easily because we know the physics of atoms and photons very well. So we can calculate this sound horizon, and from that we can estimate the position of the peaks in the angular power spectrum. Any questions there? Sorry? Multiple moments. The multiple moments. Here. Because this is called the cosmic covariance. Because there are so many, there are few measurements of these scales that you cannot reduce the error in the measure. That's why. Yes, the physical significance is that we only see one universe. In order to have a better measurement here, we would have to observe many universes to have more measurements of the cosmic activity. But unfortunately, we only see one universe. That's, so to speak, the answer to that question. Well, from the peaks in the angular power spectrum, we can infer a lot of information. So, the most important here is the position, the location of the first peak in the angular power spectrum. This peak, the location of this peak, helps us to measure the curvature of the universe. If the universe is open, this peak should move to the right. If the universe is closed, this peak should move to the left. And if the universe is flat, should be located at the very definite multiple moments here. So the first measurement of the position of this peak was made in 2000, something like 17 years ago, when they measured the position of this point, and they found that the location of this point was exactly at the very value of the multiple moment that indicates that the universe is flat. So from here you can calculate the curvature of the universe, and the experimental number, so to speak, is what it is here. It's 9 times 10 to the minus 4. Wow. If the universe is flat, this quantity should be 0 exactly, right? But wow, experimentally, observationally, it is not exactly 0 because you have some errors in the measurement. But it is very close to 0. And actually, we believe that if we try to do a better measurement of this location of the first peak, this quantity is going to become smaller, even smaller than this number. So the cosmological community believes that the universe, that you can essentially say that the universe is flat, that its curvature is 0. So this is one answer to it. Well, there was one question before. This is the answer. It comes from the location of this. I mean, the universe is flat, which means that if you want to do any measurement very large measurement in the universe about distances and triangles and spheres and circles and whatever, you only have to apply the same rules as in Euclidean geometry. If you try to draw a very large triangle in the universe, the sum of the internal angles of that triangle should be what angle? 180 degrees. Exactly. Okay, so you look a little bit disappointed because of this. Probably you wanted the universe to be closed, right? Like Einstein's belief. Or probably you wanted the universe to be open. But no, it is the simplest of all possibilities. The universe is flat. Just to remember you about the implications for this, let's go back to the Einstein equation. That means that this number here, for the full history of the evolution of the universe, has been exactly 1. For all the evolution of the universe. I'm talking here about 13, almost 14 billion years of evolution, and this number has been 1 for all that time. Exactly. That's another mystery in cosmology. Why this number was set up as 1 as an initial condition for the expansion of the universe. Nobody knows why. Nobody knows what is the reason behind this. But it is exactly 1. So that's a mystery that probably you will have to solve if you become cosmologists in the future.
Do you have a definition for flat? For me, flat is flat.
Flatness, but I'm not talking about flatness in 2 dimensions. I'm talking about flatness in 3 dimensions. And that means that the rules for measurements of distances and whatever for any geometry in 3 dimensions are given by the rules of Euclidean geometry. That's the definition of flatness in 3 dimensions. That you have to apply the same rules that you were taught in your primary school, your primary studies. You don't have to learn any other geometry from now on. That's the only one. Okay, and from this figure there is another measurement which is very important. From the difference in the height of this first peak and the second peak, the difference in the height gives you information about this ratio here. If this ratio is very large, so the difference between the 2 peaks is very small. But if this ratio is small, the difference between the peaks is large. So by measuring this height, the difference in height, you can measure this quantity. And from this, you can calculate how many atoms per photon there are in the universe. And the number is this one. So this is just the normalized density in atoms with respect to the total energy density in the universe. And this means that the present contents of atoms in the universe is just 4.9% of the total matter budget in the universe. So the atoms are only 4.9% of the total budget. They are not a 100%. They are only 4.9% of the whole universe. So the type of matter that we are made of is not important in this field. It is a very tiny fraction. Oh, not very tiny, but it is a tiny fraction, right? So probably this is the answer to the last question, right? this is kind of ironic, right? Because we understand very well the physics for atoms and photons and neutrinos and so on. And we are very proud of that. Probably you have heard that the standard model particle physics is one of the most successful theories in physics, in the history of physics, right? Yeah, it is very successful, but it is not enough to explain the matter values of the universe. It is just able to explain 4.9% of the matter of the universe. So we have something very hard ahead. Any questions? Okay, so let me show you how this is done in reality. Probably you are thinking about how do you do that? How do you do all the calculations? Probably I'm just talking about a cartoon picture of the universe, but I'm going to show you how the real calculations are done in real life, in the real life of a cosmologist. Right. So let me try to change this. So in order to calculate the anisotropies in the microwave background radiation, we have to do everything numerically, using numerical codes. One of these codes, well, they are called Boltzmann codes, because what they do is to solve the Boltzmann equation for photons. But the calculations are very large, and they cannot be done analytically. So everything has to be done numerically. So this is one type of these Boltzmann codes, which is the class code, and it is written in C, in the language C, and it has all these files to solve. So the important things in the file, the numerical codes are these routines here. You can see that there are many names here: background, input, lancing, nonlinear, output, perturbations, primordial, spectra, thermodynamics, and transfer. So you have to calculate all these quantities in order to have a good theoretical prediction for the anisotropies in the cosmic microwave background. Let me show you the part of the numerical code that solves the Einstein equations for the background, for the equations that we were discussing yesterday. It is this one. Okay, so the number of lines is on the left. I'm going to go to the last part of the numerical code. So the number of lines here is 2097. Well, 2098 if you take this last line here. And this is just one part of the numerical code. And the rest of the routines are more or less the same size. So in order to give a good theoretical prediction for the anisotropies, you have to understand how this type of numerical codes work. And you can see that this is a very difficult task. Right? So this is a real life. Fortunately for cosmologists, this numerical code is a very efficient one. So the runs last for just about 1 second. So with just one click, and you only wait for 1 second, and you will have a prediction of your model. But you have to understand. So this is the real thing. So the equations I have shown to you, they are not the full equations that we usually solve in daily life. They are much more difficult. Any questions? So that was just an example. Oh, let me go back. I want to show you the input for this. Well, this is the input parameter file for the numerical code here. So there is a lot of information that you have to provide in order to have a theoretical prediction from your model. So there are, you can give the code the Hubble parameter, the photon density, the baryon density, and many other things here. And the list goes and goes on and goes on and goes on and goes on. So this is the input file. So you have to give precise information of every of the parameters here in order for the numerical code to understand what you are trying to do. And this is again real. Okay, let me go back to the slides. Do you have any questions? Yes, they are publicly available. Actually, this numerical code was made by the Planck Foundation. They were released publicly for the whole community. Yeah, you only, for instance, you write down class code in Google. Yeah, but after the session, I can give you some extra information. Any other questions? Huh? All right. So I'm going to skip this. Sorry, I'm going to skip all of this because I don't have a lot of time. But so let's go to the next point. Okay, so let's go to the next important thing in the project, the accelerated expansion of the universe. Right? So there was a very famous measurement of the distances of supernovae happening in other galaxies, and the astronomers were able to measure the distance to every of these supernovae, and they tried to figure out what is the best topology to explain the distances to these supernovae. Okay, I'm going back again to this calculation at the beginning. Remember that in order to calculate the proper distance here, you have to do an integral here, which was dE over A, right? So the answer to this proper distance to different objects in the universe depends on the solution for this scale factor function. But in order to know this scale factor function, you have to know the ingredients, the matter ingredients, so that you can also solve the Einstein equation. Right? So the answer to this, I mean, the result for this proper distance will depend on your model of preference. You have a favorite model, there will be a prediction for this proper distance. If you choose any other model, there will be a different prediction. So you can compare those predictions to the measurements. Here, what you see in the figures are observational points for different supernovae happening in different galaxies in the universe. On the vertical axis, it is, so to speak, the difference between the measured distance and the theoretical distance. The difference between the two. So if the theoretical model is the right one, all the points should be around 0, right? Because in that case, the two distances, the measured one and the theoretical one, are the same. But because this is an experiment, this is real life, well, this is not very clear if everything is just around 0, right? And you can see also that there are many large errors in the measurement. Another important thing here is the horizontal axis. The horizontal axis is just a redshift of the light coming from every supernova. So this supernova here are coming from a redshift of around 0. That means that they are very close to the Milky Way. But the farthest supernova is this one here with a redshift of 1.4, another one here for 1.4. That means that the universe at that point, just remember that the scale factor is 1/1 plus the redshift. The redshift is around 1.4, let's say 1/2.5, right? This is more or less how much? 1.4. More or less, right? Okay, not good at doing these calculations. So when this supernova exploded, the universe was more or less 1/4 of its actual size. That's the meaning of this number here. It was just 1/4 of its size at that point when that supernova exploded. So you can make a conversion of these quantities into distances, or into the scale factor, or even into time. For instance, this is a very illustrative figure published in 2003 by one of the discoverers of this acceleration of the universe. And at that time, there were very few points, observational points for supernovae. You can see that these are just a few observational points. This is the axis of time, so we are here today. In this direction, to the left is the past, and to the right is the future. So, in terms of time, the farthest supernova recorded here exploded at around 8 or 9 billion years ago. So we are detecting the light of a supernova that exploded a very, very long time. Well, probably you agree with me that 8 billion years, 9 billion years is a very long time. Right? But we are detecting the light from that explosion. And we are using that to measure the distance to that supernova. This is the scale factor again. This is the redshift, so there is a correspondence between redshift, so the scale factor and the redshift. And the different lines here are different models for the universe. So what you have to do is to solve Einstein equations and give a prediction for every year. So it is very clear, even in this figure, which is not scientific, technically, it is not, how can I say that, it is not technically strict, so to speak. And you can see that the preferred theoretical curves, according to the observational points, correspond to accelerated universes. Universes that first accelerated, and then from some time afterwards, they accelerated their expansion. So there is a very clear preference for accelerated universe. So this was very important. Just by measuring the distances to supernovae exploding in different galaxies, you are able to determine what is the best model to describe the evolution. And in this case, this was important because it is suggesting that the universe is right now accelerating. And if you try to follow, for instance, this dark green curve over here, you will see that for the future, this universe is going to expand forever and ever in an accelerated way. So this was a very, very important discovery. They were given the Nobel Prize in 2011 for this discovery of the accelerated expansion. Please be aware that I'm not saying that they discovered dark energy. No, they discovered the accelerated expansion. Okay, this was very surprising, because if you believe that the universe is only made of atoms, an accelerated expansion is never possible. So that's why there is a suggestion if, okay, if there is an accelerated expansion and the baryons and the atoms are not a full matter budget, so there must be something else that is making the universe accelerate. Right? Okay. There are more technical details here. If you, well, just to show you quickly how this is done. What you have to do is an expansion, a Taylor expansion in terms of the redshift of the distances to this supernovae. Do not worry about the details how to get this equation. But roughly speaking, this is the distance to the supernovae in terms of the redshift. You have a Taylor expansion in terms of the redshift up to the second order here, or up to the third order, because the first order, the smallest order is the linear one. So what you have to do is to try to calculate the different coefficients in the expansion. You can notice that the first coefficient in the expansion is just a Hubble complete. So this supernovae data can also be used to calculate the Hubble parameter at the present time. And this is important because from that we can calculate the age and the size of the universe. Right? So it is the first term in the expansion. And the second term in the expansion is called the deceleration coefficient. Here. So what they were able to do was to measure this quantity. But there are other quantities in expansion. This is, for instance, this is called the jerk, and there are others with snap and whatever. So, so far, we haven't been able to measure this quantity because the data is not good enough to do that. We can only measure the second coefficient, the first and the second coefficient. And
yeah. So H0 is going to be a fixed value from the observation. H0.
Yes.
But what observation? Because there's, I mean, tension between local observation for the value of the present Hubble and from observation of tsunami, for example. So
yeah,
that numerical value is going to change the distance. I suppose.
Yeah, because that's the origin of the tension. But the good thing here is that you have two independent measurements. One coming from cosmology, from the cosmic microwave anisotropy, and the other one coming from distances to supernovae. The important thing here is that there are two independent measurements. They are in tension now. Nobody knows why. But well, we believe that this is going to be resolved soon. Okay, these are the numbers that are reported. You can see that they are good enough and experimentally. Well, there are. I mentioned before that there are different definitions of distances according to general relativity. So the astronomers can use many of these different definitions of distances, and from these distances they can calculate the acceleration parameter. If the acceleration parameter is negative always, with a very significant, this is a significant measurement of the acceleration parameter. It's negative. This means that the universe is accelerating because, for historical reasons, this parameter here was defined so that an accelerating universe corresponds to a positive quantity. So, if this quantity is negative, means that the universe is accelerating. Any question? Okay, let's go to almost to the last one, important block in the evolution of the universe, the so-called dark matter. Okay, what is the origin for this dark matter concept in cosmology? Well, probably we can go back to 1995 to this paper. They were asking this question, where is the dark matter? And what they tried to do was to measure the amount of matter at different scales in the universe. So the process was more or less like the following. Imagine that you are able to measure the matter inside a given volume. You know, you are able to measure the mass inside this one. And you are also able to measure the luminosity coming from this region, of the light coming from this region. The luminosity, the mass, and the luminosity. So what you can try to calculate is the ratio, the mass to light ratio, this one. Right? So in order to have a value of reference, you can use the sun. So you define that the mass of the sun over the luminosity of the sun should be 1. Right? So for instance, if you detect that here you find that the luminosity is 1000 of the sun, right? And there are many stars here. So your expectation is that the mass contained here should be around 1000 solar masses. This is a reasonable expectation, right? Because all the light is coming from the stars. And the stars are very similar to the sun. So if the luminosity is 1000 times that of the sun, you're expecting that the mass is roughly 1000 that of the sun. Right? So but they decided to do this experiment, but with even larger and larger volumes in the universe. This is shown in this case. So this is the mass to light ratio in units of the mass to light ratio for the sun. And this is the radius of the volumes in terms of megaparsec. 1 megaparsec is around 3 million light years. So it is a very large radius, right? And they try to do that for different radius, different volumes, and they were measuring, determining this ratio. So you can see that for the volumes which are very small, or for small volume, there is more or less a linear relationship here on logarithmic scale, which means that you are expecting to have a ratio very similar to that of the sun. But what happens? There is a plateau over here, right? Well, you can make an interpretation of this plateau over here in terms of the quantity of matter that you can find everywhere in the universe. An estimation of the total amount of matter. If this plateau appears in your figure, for instance, for this case, it means that only 30% of the universe is made of matter. Only 30% of the universe. And this is just a direct measurement of the matter that is contained in different volumes in the universe. And the result from here is that only 30% of the universe is made of matter. If the matter were the 100% here, so that the observational point should be reaching this point over here in the figure, but they are not. So it is only 30%, no more. So this was a first indication that there is something else apart from matter in order to fill in the whole matter budget in the region. So of this 30%, 4.9% is just the atoms that we already got. So even within this 30%, there is some 25% that we don't know what is about. And that's what we call dark matter. Because it is not giving us any light signal of its existence. So far, so good. So 4.9 for atoms, 4.9% for atoms, 25% for atoms, and 0%. So the question is, what is the rest? The rest is 70% of the matter. And but the first question is, how do we know that there should be some 70% in addition to this matter content? How do we know that? Well, the answer is very, very easy. The answer is this one. Because this number should be equal to 1, it means that we have to find the 100% matter budget in the universe. If the universe were open, so that this quantity was negative, and we found that we have already found 30% of the total matter, probably that wouldn't be enough. We don't need to search for more. 30% is just. But because this quantity should be equal to 1 according to the measurement of the entropy of the cosmic microwave, we have to find the full 100% of the matter. And so far, doing measurements of the nucleosynthesis process, doing measurements of the matter contents in different volumes in the universe, we can only fill up 30%. So we have to find the 70% extra to fulfill this constraint equation. Any questions here? Okay. Let me see. Where's the time? Okay, I'm going to close with the last slides. There are many details I can tell you about, but let me continue here. So this is a table that the Planck collaboration released in 2015 about the measurement of different cosmological points. And for instance, this is the number they found for the age of the universe. So these numbers are obtained by making a very careful comparison between the theoretical models and the measurements at the different cosmological measurements, different cosmological observations. And for instance, they are reporting, well, there are different combinations of the data sets, but you can see that the number they are reporting here, they suggest that we should take this, the third column, or as you remember. Is that right? Okay, that's the third column. So the age of the universe is 13 billion plus 796 million years. Right? Plus minus 0.0. So I hope that you are amazed by this, because they are giving you the age of the universe with 3 significant figures. Right? This is a serious measurement of the age of the universe. So cosmology is becoming an accurate enough field of physics, and right now we are able to give numbers with this accuracy. 3 significant figures. So what is the error in the measurement here? Can you tell me what is the error in the measurement there? In million years, what is the error in the measurement? 29 million years. That's the error in the measurement of the age of the universe. When did the dinosaurs disappear from Earth? 60 million years. So the error in the measurement is less or is smaller than the time that has elapsed since the disappearance of the dinosaurs from Earth. I hope you are amazed by this. Right? This is amazing. So probably in the next measurements of the cosmological parameters, probably they are going to make this error to become smaller by 1 order of magnitude. So probably the age of the universe is going to be known by 1 plus minus 1 million. Right? Probably in the future. But this is an amazing measurement. And apart from that, they also measure the matter content of the universe. So I'm going again to the third column here. So you can see that the matter contents of the universe should be around 30.65%. And again, they are giving you the answer with 4 significant figures. Or 3 significant figures. And for the other part of the matter budget, they are telling us that there might be something like 35% of something that we call generically as dark energy, but here we are referring to that dark energy as the cosmology. So they are suggesting that the best model of the universe should have all these numbers. So these numbers, these quantities that appear here, are some of the quantities that I showed you before that are calculated in this numerical code, very numerical code that makes everything for every model of the universe. So this is quite amazing. This is more or less the chemical table of elements, the modern one. So you have the things that we already know are over here, and the rest is dark matter and dark energy. Well, I think that this is a good point to finish the session. Okay, thank you.